Hey everybody, welcome back to Complex Analysis. So recall from the last video, we finally have our big long list of ways of thinking about complex numbers. So the first way we can think about a complex number is what your book calls rectangular form, or I was calling it in a previous video, the regular old number form. We can also think about complex numbers as points in R2, which now me and your book, we've decided to agree to disagree here. I think about this as the same as the vector form, but your book actually sort of distinguishes those two. By the way, that was a joke, everyone. Your professor is not talking to inanimate objects. In any case, we can think about complex numbers as living in two-dimensional space, or we can think about it as a vector starting from the origin and going to wherever the point is. 3, we have the polar coordinate representation, so kind of taking from Calc 3 a little bit. Remember, instead of viewing points as living on a rectangle, we can think about points as living on a circle of radius r, whose angle with the positive real axis is phi. Okay, so this would be our polar representation. And then finally, Trig gave us another way of thinking about complex numbers, and that's exponential form. Exp form. Okay, so hopefully you guys have seen this or sort of realized this. Notice that the first two are very, very related to each other. So is the last two. Okay, now today we're going to shift gears a little bit. We're going to be talking about geometric properties of complex numbers. And we're going to talk about the famous triangle inequality today. So let's go ahead and get started. So we're going to start with some inequalities that aren't really too hard to see why they're true. And these inequalities are going to give us bounds on our real and imaginary parts. So let z be any complex number, so x plus iy. Remember, x is what we call the real part, and then y is called the imaginary part. Okay. So given a complex number, then we have that the following inequalities hold. I'm going to walk you through the first one. The second one is pretty much exactly the same. So let's see how we get this first one. Now, this is one of those times where in mathematics, it's actually pretty nice just to walk through from left to right. In any case, how we get this inequality is as follows. So first of all, the minus the absolute value of negative z by definition is equal to minus square root of x squared plus y squared. Okay, hopefully that makes sense. That's just coming straight from definition. This part here is certainly equal to this part. That's how we find the modulus. Okay, now notice that this number is a negative number, right? We have x squared plus y squared on the inside of a square root. So we know that that's going to be positive, and then we have a negative on the outside. So this is certainly going to be less than or equal to, since y squared is positive and the whole number is negative, we know that this is less than or equal to minus square root of x squared. Okay, because if we get rid of y squared, we're making it a less negative number. So if we think about a number line, we're making it possibly something like this, where maybe square root of x squared plus y squared is 3, and square root of x squared is 2 or something, so that we get, when we put negative signs, that this one is less than or equal to this one. Okay. Now, negative square root of x squared, this is equal to, by definition, negative absolute value of x. So, of course, that's going to be less than or equal to x. It could be equal, depends on if x is negative or not, but that's certainly less than or equal to x. Likewise, x is less than or equal to the absolute value of x, and again, that depends on whether x is positive or negative, okay, whether or not equality holds, I should say, but that's equal to square root of x squared by definition, okay? And then lastly, this is certainly less than or equal to, so if we take x squared here and we add something positive underneath the square root, okay, we certainly have this inequality here. So this is how we argue or we develop these inequalities here. And it's the same thing with y. Actually, it's exactly the same thing as y. There's nothing that's really changing there. Now remember, since x and y are the real and imaginary parts, that gives us the following inequalities here. So we know that minus the length of z is less than or equal to the real part of z is less than or equal to the length of z, and likewise for the imaginary part. So what this is telling us is that the real part of your complex number and the imaginary part of your complex number can only be as big as its length and is certainly greater than negative its length. Okay, or that's the least it could be in a way. Okay, so we're going to define something that you may have seen before, and this is something that kind of comes up in calculus, although we don't deal with complex numbers in calculus, but we do deal with something called the conjugate, if you guys remember the limits. Now, where the conjugate comes from, it really comes from a nice property of the square of a modulus. So if we take z equal to x plus iy, okay, the length of z squared, okay, so the square of a modulus complex number is equal to x squared plus y squared. Okay. Now you might be like, okay, yeah, sure, that seems right, because if you square a square root, the square root goes away, right? But this is also equal to the following. Okay, so x squared plus y squared is equal to x plus iy times x minus iy, and we're really playing on the fact here that I squared is equal to -1. That's why we get a plus y squared in the end. Now, because of this, and this number here on the right shows up a lot, we have a special name for it. This number here, this complex number here, is what we call the conjugate. Okay, so definition, x minus iy is the complex conjugate of x plus iy. Okay, and we usually denote conjugates with this bar, this horizontal bar here. So the complex conjugate of x plus iy is equal to x minus iy. So basically all you're doing is you're taking the imaginary part and you're changing the sign. Okay, so the conjugate changes the sign of the imaginary part. Okay. Now, what's happening geometrically when you take the conjugate? So let's say we have, I'll draw this kind of small. Let's say we're considering the complex number 1 plus I. Okay. So the complex conjugate of 1 plus I is equal to, so remember you just changed the sign of the imaginary part, this is 1 minus I. Okay. So what happens when we graph this? 1 minus I will be right here. Okay, so geometrically, conjugation is just taking points and reflecting them over our real axis here. It's taking this point in this case and flipping it over here. Okay, so geometrically, that's what's happening with conjugation. We're reflecting over the real axis. And we have a lot of nice properties with conjugation, which some of them will probably make sense. And we're going to actually prove one of them today, and I recommend everyone you should prove or try to prove all the other ones as well. So they're not too bad. They're pretty nice. So the first property says that if you're taking the conjugate of a sum or difference of two complex numbers, then the conjugate distributes over that sum. Okay. Part B here is saying if you take the conjugate of a product of complex numbers, then again the conjugate distributes over the product. C, similar, if you take the conjugate of the quotient of two complex numbers, then the conjugate distributes over the quotient. Okay. D, if you take the conjugate of the conjugate, you get what you started out with. Okay, which hopefully makes sense, right? If you take x plus iy and you conjugate that, you get x minus iy. Now, if you conjugate that again, what do you get? You're just going to get x plus iy. So you get what you started out with. Part E says that if you take the length of a conjugate, you still get the length of the original complex number, which should make sense, right? Let me go back to our picture here. If we think about this example I have here at the bottom, notice the lengths are preserved, right? All we're doing is we're reflecting, right? So that means that the lengths of our complex numbers are being preserved under the under conjugation or under the complex conjugate. F, if you take the square of the length of a complex number, it's equal to the complex number times its conjugate, which we already saw that. Remember, that was that x plus iy times x minus iy equals x squared plus y squared business. Okay. G says that the real part of z is equal to 1/2 z plus the conjugate of z. Okay. And then H says the imaginary part is 1/2I times z minus the conjugate of z. Okay. And then lastly, if you have a complex number in exponential form, okay, and you take its conjugate, all you have to do is take the negative of its argument. Okay. And that should make sense again, because remember, conjugation is not affecting the length. It's just affecting the sort of its position either in the with respect to the real axis. Okay, so let's actually prove one of these. We're going to prove part A. Remember, part A said that if you take the conjugate of a sum or difference of two complex numbers, then the conjugate distributes over that sum or difference. So today we're going to actually prove the sum part. The difference part is virtually the same. So proof. Let's let z1 equal x1 plus I y1, z2 equal x2 plus I y2. Okay. All right. So let's go ahead and prove this equality here, though. This is our goal. Okay. So let's start by taking the conjugate of z1 plus z2. Okay, so the conjugate of z1 plus z2, well, before we take the conjugate, let's go ahead and substitute. What do we know about z1 and z2 here? This is going to be x1 plus iy1 plus x2 plus iy2. Okay, I'm going to go ahead and combine my real parts and imaginary parts. So this is the same as x1 plus x2 plus I times y1 plus y2. So just doing a little bit of factoring there and grouping. Okay. So now we can take the conjugate, though, because now we have our real part, imaginary part. And remember, all the conjugate does is it changes the sign of your imaginary part. So we're going to get x1 plus x2 minus I times y1 plus y2. Okay. Now let's simplify this a little bit. So I'm going to go ahead and redistribute I and group together terms. So this will become x1 minus iy1 plus x2 minus iy2. And notice, what is this quantity right here? Okay, this is the complex conjugate of z1. So this equals z1 bar. And similarly, hopefully you guys recognize the second quantity here. That's going to be the complex conjugate of z2. Boom. So we have that the complex conjugate of the sum of two numbers, complex numbers, is equal to the complex conjugate, or I should say the sum of the complex conjugates of those complex numbers. Kind of a mouthful there. Okay, but again, notice that the complex conjugate is distributing over a sum. Now again, for differences, it's virtually the same proof. I recommend you try that at this point. Try to mimic this proof. Oops, and let me go ahead and end my end of proof symbol there. Okay. So we're not going to prove this. Your book does, I think, a pretty good job of proving this for you, so go ahead and read that. But in any case, we have what's called the famous geometric inequality, i.e. the triangle inequality. So the triangle inequality says the following. For any two complex numbers, we have that the length of the sum is less than or equal to the sum of the lengths. Okay, so length of sum is less than or equal to the sum of the lengths. Okay. Now the reason why this inequality is true, at least geometrically, because remember this video is supposed to be on geometry, it's really coming from a triangle. And I'll show you how that works. So let's say Z2 is here. I'm going to try to change colors really quick. Yeah, there we go. I like green. It's nice to have that. Let's see. So let's call this Z2, and let's call, I don't know, this vector Z1. Okay. Now, what happens when we take the sum of z1 plus z2? So let's think about that geometrically. So we're kind of taking our cues here from Calc 3 a little bit. So when I geometrically add vectors, remember all we have to do, if you guys remember, it's the tip to tail method, right? So I'm going to draw z1 so that its tail is at the end of z2. Okay, and then to find the sum of these two vectors, we just connect the tail of z2 with the tip of z1. Okay, so this vector in the diagonal here, this is going to be the vector z1 plus z2. Okay, now notice, here let me use a different color. We have a triangle, right? We have a triangle whose legs are length of z1, length of z2, and whose hypotenuse is the length of z1 plus z2. So what do we know about triangles back from geometry? We always know that the length of the hypotenuse is going to be less than or equal to the length of the sides. So that's what this triangle inequality is saying. It's saying that the length of the hypotenuse is less than or equal to the sum of the lengths of the remaining sides. And I just realized that blue on blue is probably not the best idea there, but hopefully you guys can read that okay. So again, the length of the hypotenuse is less than or equal to the sum of the lengths of the remaining sides. So that's what the triangle inequality is saying there. Now, to prove that, you have to be a little bit more clever with your absolute values and stuff, so read the book for that. But I wanted to give you sort of the intuition behind it. And why do we call it the triangle inequality? Well, hopefully that's fairly evident from, well, we got a triangle going on here, right? So a way of interpreting this is in terms of a triangle. Now, from the triangle inequality, we do actually get a couple more properties as well. So A here in corollary 1.7 is just the triangle inequality, but we've generalized it to plus or minus z1 plus or minus z2. We still get the same sort of relation. Part C here is saying if you take the sum, so let's say we have the sum of z1 plus z2 plus z3, for instance, this is still going to be less than or equal to the length of z1 plus the length of z2 plus the length of z3. Okay, and it's true for any sum of complex numbers. So if I had 4, we would still get a similar thing. For instance, z4. Okay, now B here is a little bit more interesting. This is what we call the reverse triangle inequality. So let me go back to our picture here. Let me change from blue. So the reverse triangle inequality sort of tells us something about the difference. So in the regular triangle inequality, this was telling us that the length of the hypotenuse is less than or equal to the sum of the lengths of the remaining sides. Well, what about the difference of the remaining sides? Okay, so if we go back to our picture here, if you wanted to calculate z1 minus z2, okay, you would get the following vector. So here's minus z2. Okay, so the vector we would get in this case, whoops. Again, using the what's called the tail tip method. So here's minus z2. So there's z1 minus z2 there. Okay, this vector right here. Okay, so what I want you guys to do, and this is actually an okay picture with respect to the lengths, but notice that z1 plus z2 here, which I'm going to redraw, is this vector. And we have z1 minus z2 now. I want you guys to think between this vector right here and this vector right here, which one has the biggest length? Okay, so take a second, look at them. Now hopefully you realize that this one up here, that has the bigger length, and that's what the reverse triangle inequality is saying. It's saying that the length of the hypotenuse, okay, is going to be greater than or equal to the difference of the remaining sides. or the lengths of the difference of the remaining, sort of mouthful, the difference of the remaining sides. Okay, so if we go back to our statement, that's exactly what this is saying right here. So the length of our hypotenuse is greater than or equal to the difference of our lengths of the remaining sides. Okay, and that's a quick video on some geometrical properties of complex numbers. Bye-bye.